I'm sorry I was muted. Yeah. Good evening, Williams. It's good to have you. Bashir, good evening. Timilayan and Christian, good evening also. Okay. So we'll start now. Can everybody see my screen? The whiteboard.
Oh, yes, sir.
You can see it, right?
Yeah.
Yeah, so I just have y equals a naught plus a1 times x1. Okay. So we're going to do a simple example of machine learning with regression, and then we're going to see a few features of it just now. Okay. So the last time we met, okay, so I'm going to start to share. So what I want to do is I'll show you the way I start it. So I go to start. Because I've done Anaconda Navigator before, I won't repeat going to Anaconda Navigator. I can go to Jupyter Notebook directly, and it's going to open a notebook for me. It takes a little bit of time, but it's going to pop open. And then in this case, you will see how I will go to a particular folder and work in that folder. So you're going to open a browser for me, and then the Jupyter Notebook will be opened. So it uses your default browser, whatever it is. Okay, so it has come. So I'm going to go to a new folder because I want to go to a different folder. So the folder I want to go to is in documents. And in document, I think I want to go to Python intro 2. And then I want to take a look at this file, April 30, 2025. Okay, so I double click it. It opens the Python notebook. So I think this was the last thing we did on Wednesday. So I'm going to show you how to drop a column. So I import pandas as PD. And then this data set, I'm going to read it. So it's still importing. I know it's still importing pandas as PD because there's an asterisk step. Okay. And then this PD, I'm going to read this data set. And I think the next thing is you can do describe and everything. But what I want to do is I want to go to the place where I created many rows. Okay. So I'm good. So this twice enrollment, I created this as DF enrollment start 2. And if you go down also, so if you head it, it's going to have this extra column which says twice enrollment. Okay. Then also the last time we saw that you can multiply two columns together. You can subtract, you can do different things. You can raise 1 to 1 power, different things. So I did this and it gave me, and then if you print it, it gives you this. So this original columns, module ID, instructor, TA, enrollment rating. Then this twice enrollment is the one I added. And I also added this rating star enrollment. Okay. What if I want to remove this twice enrollment column? I want to get rid of it. Okay. So you can do that easily. So here, so what I'm going to do is, if you do this tf dot drop, uh, Then I'm going to tell you what to drop. I'm going to tell it. Oh, let's first do df dot columns. So we print the columns. Um, so this is a column. It has module ID, instructor, TA, enrollment, rating, twice enrollment, rating, enrollment. So the column I want to drop is twice enrollment. Okay, so I'm going to copy it exactly. The reason I did this was because sometimes when you see something, you may not know there may be a space here, and you don't know that there's a space. Okay, so if you don't know that there's a space and you just say, let me copy a rating, but there's a space, then it's going to give you an error. So it's better to write out the columns. Then once the columns are written out, then you can drop the one you want to do. You want to drop. So if I do dot drop, the one I want to drop is twice enrollment. And then I want to drop the column. So I'll tell you that the axis is one. If you do this, it doesn't drop the column. It will just write for you a new data frame. Okay. So this returns a new data frame, okay, when the column you wanted has been dropped. Okay. But where is this new data frame? It does not exist anywhere. So what you have to do is you should put this new data frame, is to put it in a new DF. Let's call it DF5. So I drop twice enrollment. Axis is one, means I drop it by the column. I do shift return. So now if I print, so I'm going to print now, DF. So the DF will still have all the columns that they had, okay, because I didn't change DF. So you still have twice enrollment and rating times enrollment. Okay. But what I can do is I can print DF5, and DF5 does not have the twice enrollment column because I dropped it from the column. So this is how you drop a particular column that you don't want. You can also drop a row that you don't want also. Okay, so this is how you drop the column that you don't. So if I had like 500 columns, doesn't make sense for me to, and I only, and there's one column I don't want. Doesn't make sense for me to drop all the 500. I mean, doesn't make sense for me to input all the 499 that I want. I can just drop the one I don't want. So this is that. Okay, so for today, I'll tell you a little bit about scaling, and then we will take the data that we have. Actually, 614. Yeah, I'll tell you a little bit about scaling, and then we'll take the data that we have and we do a simple linear regression on it, and we do a little bit of an advanced linear regression. So I'm going to go to the home here. Let me hide. So I go to home and I do a new Python, and I'm going to rename it to this date. So go to file. Actually, there should be a way for me to view. Not out for this. Okay, I'll find out how to do it later. So I'm going to go to file, I'm going to rename. And today's name to, okay. So I'm just going to show you how to use this standard scalar. Sometimes it's useful, especially when you do SVM and you want to actually it's useful in all cases, because if you print the coefficients, and then it can tell you, if you look at the coefficients, it can tell you which coefficients are most important. Okay, so you will see from sklearn pre-processing input standard scale. What the standard scalar does is to scale so that mean is 0, standard deviation is 1. Okay, so it's going to scale the data you have so that the mean is 0, the standard deviation is 1. There are other ones that you can have also. So standard scalar scale so that mean is this. There's min max scalar, which you can use also, and it scales so that all values lie between -1 and +1. So it's going to find the maximum and it's going to find the minimum. So it's going to do something like, okay, standard scalar, what it does is it does your value minus the mean. It's going to calculate the mean. It divides by the standard deviation. Okay. Standard deviation is square root of the variance. So this is what it does, x scaled with this. The min max scalar, what it does is x scaled is x minus x mean minus the minimum, okay, over max minus minimum. Okay. So this is what x scaled does. This is what MMS does. I'm importing both of them together. Sorry, input, not import, not input. Import. So it imports both of them, not input. From sklearn is import standard scalar and min max scalar also. So that happened. Okay. Let's create a data frame that we will use. So I'm going to, yes, we could use the data frame that we already had, but let's create one that we yeah, okay. Let's create one that we can, just to show. Okay, so I say pd.data frame. Okay. So one way to create a data frame is to, apart from reading it, is to create a dictionary. Okay. So if you create a dictionary, it turns out that the key, a dictionary of list, turns out that the key will be the columns and the elements will be the rows. Okay, so this call it A. So that's the key, and then the values is this list 1, 2, 3. So this A like this is the first element in the dictionary. Then create another one I call B. So B is the key, and the values is another list 11, 8, 3. These are the values, and then you can create another one. So this will create a data frame. So one way to create a data frame is just to create a dictionary with the column name as the key, and then the values as the list. Okay. So I can do this, and if you want, you can. Oh, yeah. So I read the error. It says name PD is not defined. Okay. Who knows what happened? Why did you tell me this, that name PD is not defined?
You didn't
I
import
didn't
pandas.
pandas.
I don't
You
think
didn't
we have
import pandas.
imported
Yeah,
pandas.
I didn't import pandas. Yeah. Um, so let's import pandas. I could import it together with this, but let's import it separately. So I'm just going to import. So I've imported pandas now, and then I can create the data frame. And then I can print the data frame, so we'll see how it is. So the data frame, the first column is A, the second column is B, and it has A has 1, 2, 3, 2, B has 11, 1, 8. Okay. So the next thing when you're using a scalar, when you're scaling, is you instantiate an object of that class. So I'll just say SC. So this is the name I choose, and then I can import it. I can import standard scalar. I can instantiate standard scalar. Okay. So this will instantiate standard scalar, and then I can use it for the data frame. So what this sc.fit df does, it's not a fit, okay? But what it does is it's going to take the data that I have in df, and it's going to apply this rule that I have here. X scaled is x minus mean over st, and x scaled, yeah, this rule that I have here is going to apply it to it, okay? So if I do this and I fit it, okay, oh, sorry, no, sorry. It doesn't do that yet. What this does now is it's going to calculate the standard deviation for each column and the mean for each column. This is what this fit does, okay? So it will create the standard deviation for each column and the mean for each column, okay? So this is what this sc.fit df does. So if you want, I can print the standard deviation, sorry, the mean, and I can print the standard deviation. Actually, this will print the variance. And then the standard deviation is the square root of the variance. Okay. So this 2, 5.75, this 2 is this mean for the first column. This is the mean for the second column. Okay. This is this variance for the first column. This is the variance for the second column. If you like, I could have done them in 2 lines. Then print also. So in this case, it will first print the mean. So this is for the first column. This is the mean for the second column. And then the next line prints the variance. This is the variance for the first column and the variance for the second column. Okay. So that is what this fit does. Okay. Now, to scale my values, I will have to apply this transformation. After I've done the fit, which is just to calculate the mean and the variance, I do the transform on df. Okay, so this is what it produces. This first column, so this is like a numpy array. Okay, this first column is the x values. So what it returns is an numpy array, so or nd array. So I don't have a df anymore. Okay, actually I need to check this. So this column is x minus mean over variance. Okay, and this column is x minus mean over variance for B. Okay, so I've scaled A and I've scaled B. Okay. If you want, we can put everything in. Okay, so this does not, it returns it to the screen. It does it and returns it to the screen. But let's put it in something. I'll put it in this df scaled. Let's see that transform. So if I print, it writes exactly this. Okay, so it does the scaling this way. The only thing I'm concerned about is I did not return what do you call it? It did not return. Oh, yeah. It did not return a data frame. This is just a numpy array. So if you try to find what type it is, df scale. So it's just a numpy array. So did not return what I wanted it to return. Okay, you can do something and let it return what you want it to return. So let's try this. So I'll do this. I think what I need to do is I'll put A in the first column and I'll put B in the second column. Here also, I think I can do this. Let me try. I don't know if this will work, but let's try. So this did not do what I wanted it to do. So now what I'm trying to do is I'm just trying to take a particular section of it and try to do the transform on just that section of it. Sorry, I should be able to do this, but I don't know. Because I wanted to return a data frame that has the right, that is still, I wanted to return a pandas data frame. So I don't want it to return, maybe I need to do a fit transform. Let me try something else. Maybe here I should have called it df. Okay. I think maybe the issue was because df scaled was not a pandas data frame. So what I did now was I've changed the columns of df from what you had originally to something else. Okay. And the something else is similar to okay, what we saw before. So if I do this now, so I have a data frame okay, now, and the data frame has these things. Okay, so now I don't have a numpy array anymore. I still have a data frame. I think there's a way you can do it. So let's say here, let's go back up. So here I create the data frame. And then I'm going to copy let's do that. So I'm going to do the fit, which just calculate the standard deviation and mean. And then I'm going to do the transformation. But before I do the transformation, I'm going to create an array that looks like df. So I'm going to say, okay. So this one does the transformation. But I'm going to create an array that looks like df. So let me do that here. So let's say df2. Df.copy. I'm going to copy df into df2. And I think I should now be able to say df2 is sc.transform df. Yeah. Because I first created this array df2, which was identical to this one. So if I do df now, it still gives me the original one. If I do df2, okay, it gives me the transformed one. Okay. There's another thing you can do. You can actually, instead of doing the scaling and transform separately, there is this fit transform that can just do the fit and transform in one go. So instead of doing the fit here, and then the transform later on, yeah, I can just do the fit and transform in one go, and that will work. So let's quickly see that. Um, so let me create a third data frame. No, since this one is still there, it's fine. So what I'll do is I'm going to create a new. Okay, so now let's do that not on the standard scalar, but let's use this other scalar, min max scalar. Okay. I'll use that to illustrate it. So let's do min max scalar because min max scalar. So we instantiate an object of it. So that's what this will do. And then I'm going to create df3, which is df.copy. And then I'm going to call df3 exactly like I did before. Okay. Because min max scalar dot fit underscore transform. Okay. So it's going to do the fit and the transform together. Of df. Okay, if I do shift return now, so it does the fit and transform together. So if you do that, you are going to see that. Let's print df. Let's print df3 now. So actually, so everything lies between 0 and 1. Okay. Yeah, so it lies between 0 and 1. What did I say before? I thought I said minus 1 and 1. Yeah, it should be 0 and 1. It lies between 0 and 1. Okay. So let's print df after that. So I'm printing both df and df2. You can see that the minimum value of df is 1. Of df is 1. Okay. That got transformed to 0. The minimum value of b column was 1. That got transformed to 0. Okay. The maximum value of b was 11. That got transformed to 1. And the maximum value of a was 3. And that got transformed to 1. Okay. So it does the mapping, it does the scaling. It follows this. You don't have to do it yourself, but it does it. Okay. The good thing about scaling when you do a scaling is when you now do a regression, you can just read off the coefficients to know which term is most important. Okay, the one that has the largest value of the coefficient will be the most important. But if you don't scale at first, yes, your regression will work, but from the coefficients you can't tell which feature was most important. Okay, but if you do a linear regression, let's say your linear regression is okay, and you did the scaling before, then by just looking at the coefficients, you can tell which one is which feature is most important. Okay, so it helps in that regard. But otherwise, whether you do scaling or not, as long as your values are not too far apart, you get the same thing. Even if they are quite far apart, within numerical error, you still get the same thing. Okay, within numerical errors, you still get the same thing whether you scale or not. Well, scaling is good so that you can see from the coefficients who is most important. Okay, so now let's do this, and we're going to take a data frame. We're going to read a data frame, the housing data frame. I'm going to read CSV. I have something called data set. I think that's the name. Let me check. Yeah, data sets. And then I'm going to read this housing. Yes. Okay. This is what I sent to you. So if you do shift return, sorry, what did I do? Sorry, PD. It's pandas.read CSV. Okay, so it reads, pandas has this method called read CSV. It reads it to the frame DF. Okay, so this is what it did. So now what I do is you can find the length of the data frame, and there are 149 lines. Okay, I can do a head. It does a head. Okay, what the data frame contains is the floor area and the value of the house. So this is housing data. It contains the price of the house in thousands of dollars. So like this one is $161,000. How many square feet is 665 square feet? This one is $57,000 and it's 336 square feet. So this data I took from Jamie Chan's website. He has a website. He is very good at teaching people how to learn to code. So I just took it from his website. It's free to download. This one has the house price is $152,000 and the floor area is 673 square feet. Okay. So what we want to do now is we want to predict the value of the house from the floor area. So we are going to assume at first a linear model. So I'm going to assume first a linear model. How do I? Want to see how I show my. I did it before. I showed my. Okay, let me stop sharing. So I want to show my whiteboard. Okay, existing whiteboard. Okay. So our Y in this case is the price of the house. So we are writing it as a constant plus a variable which you need to find times the area. Okay. So x1 is the area, a0 is a constant. I don't know, the constant is maybe even if you don't buy the house, even if it has 0 square area, maybe you have to pay because you at least have to pay for the land. So maybe this is where the a0 comes in. Okay, so we don't know. Okay. But when you do the fit, it's going to find the best value of a0 and a1 to give the best prediction for you. Okay. So now that I have the data, as a scientist, one of the things I want to do is just to plot the data to see how it is and then to think of what to do next. Okay. So in this particular case, it turns out, okay, for regression, you can actually add more terms. You can add A2 times X2, A3 times X3, and you can add many terms as you want. So what I want to do first is I'll just, okay, let's take a look at the data more and maybe see if there's any missing data, maybe drop NA as we want and things like that. So let's do that. Okay, so I've done a head. I already know that there are 149 lines. So I'll print df.describe. Describe. Okay. So he printed this for me. Okay. There are exactly 149 floor areas and there are 149 values. Okay. So this data is clean. So I don't have to do any serious stuff about it. The data is clean. Even if you couldn't do this, you could check by asking if there's anything missing. So you can do this. It will tell you nothing is missing, but it's better to add up everything, and then this will tell you how many items are missing. So in this case, it tells you for floor area, nothing is missing. For value, nothing is missing. So I use this all and some that we saw before. Okay. Um, so let's do the machine learning. So at least we say we really did the test case. We're going to need to plot later. So let me import that. Matplotlib, pyplot, that's PLT. So that's, you already know. Then in scikit-learn, the linear regression model is in the subclass linear model. Okay. So from sklearn, so the way I know this usually is I just do a search. So I can, sorry. So if I do a search scikit-learn, of course you can go to scikit-learn.org, okay, but that's not the fastest because you have to be searching and everything. And then scikit-learn.org gives you all this, okay. You can check on regression and it should tell you ordinary least squares, blah, blah, this, okay. Well, usually what I do is I take a shortcut. I just do a search directly for it. So this is what I'm trying to do. Okay. So I do a search for it. I say scikit-learn. And I do linear regression. So usually I hit, you see, I hit linear regression. This is scikit-learn 1.6.1. So I don't know, because now I have scikit-learn 2 point something. So for the most part, most of the things have not changed much, but I think actually this documentation is also scikit-learn 1.6.1. Okay. So if I go here, it's pretty much the same. Well, this takes me to the place I need directly. Okay. And if you go down, there's an example for you. Okay. So import NumPy as NP from sklearn linear model equals linear regression. So I import that. Okay. And here they created their data, but we will have the data already, so we don't have to create it. And then we do a linear regression. Okay. Well, I like to do a scaling before I do the linear regression. So this is what I have. Let's do a scaling. We already imported it, so we probably don't need to import it again. But I want to do scaling with standard scaler. Then later on, you'll see that we need to split the data. So, and then you need to import something called train test split. Okay. From sklearn dot model selection. Import train test split. So we're going to split the data into training and test. And then at the end, well, not at the end, near the end, we're going to check how good our fit is. So in that case, you need a metric. Let's use the mean square error on SK9 matrix import. I think if you just do scikit-learn, RMSE, it should probably give you something about root mean squared error. So you see, so it already gave me that. And so you can use the root mean squared error directly. If you go down again, it's going to tell you how to use it again. Exactly. From skline matrix import root mean squared error. So let's use the root mean squared error. So I'll be here. Of this. So in this scikit-learn thing, at the bottom, usually they give the examples. So I have this mean squared, root mean squared error. So this is what I'll use. Okay. So I've imported all this. So what I'll do next is, so I imported it. I'll control enter. Sorry, shift enter. Okay. Then I'm going to create a series that I'll call DF. So I'm going to take the columns that I want from the data frame, and I'm going to call that my X. And the column that I want from the data frame, I'm going to call that the Y values, I'm going to call that my Y. So the floor area will be my X, and then the price will be my Y value. There are different ways to do it. So I can take the original data frame, okay, and I can drop, okay, let's list the columns first. Okay. So I want this one to be my my Y value, and I want this one to be my X value. I'm going to do that in two. So for Y, I'm going to say is DF, and I'm going to take exactly this value. So if I print Y, actually I need to know what type Y is. So Y is a data frame that has 49 lines, but it has only one column. The 149 rows and one column. I can print the type. Okay, the data frame. Okay, pandas call frame data frame. Okay. And then for X, I'm going to do it in another way. I'm just going to drop this column. I'm going to drop this column because for Y, it may be that I have several X values. Okay. And Y is only one that I need to take. X, there may be several and I want to keep them. Okay. So maybe there's floor area, then there's number of bathrooms, there's number of bedrooms. Okay. And I want to fit the value of the house as a function of all those three things. Okay. So it should be, in this case, okay, if there are three, let's say there are 50 things, okay, 50 descriptors. So I want to fit value as a function of those 50 descriptors. It will make sense for me. Okay, it will be tedious to put all the descriptors like this. Say what X is DF this descriptor, this descriptor, this descriptor. In this case, I can just drop the descriptor I don't want. Okay, so that's what I'm going to do. I'm going to say X is DF, drop. The descriptor I don't want is There's only one in this case. But let's say there were many, I'll do this. And let's see, axis equals 1. And I drop it. So I can print the type of X. Okay. And I can print also X itself. Okay. So it just contains the floor area because it dropped the Y column. So I have this Y and X. Okay. Let's scale X. So I'm going to say X scaled. Should we scale now? Okay, let's do it without scaling. Later on, I'll do a scaling and then we'll see how this works. In this case, you get the same result whether you do the scaling or not. Yeah, we'll do the scaling later. So now I'm going to split my data into training and test. Okay, so I'm going to use this train test split. I'm going to split X and I'm going to split Y. The order is important. And then I'm going to write test size is 0.2. So 20% will be test. Okay. And I'll use a random state. You choose any number, but you stick with it. Okay, let's choose 31. Okay. Any number, but any integer, you stick with it. So if you do this, it's going to return it's going to return 4 data frames. Okay. One will be the training, X training. Okay. So this X is going to split it into 2. It's going to split it into the X train and X test. Then this Y is also going to split it into 2, Y train and Y test. Okay. So everything I'm going to receive it in X. So when it does this, it's going to return yeah. So it returns this NumPy, this data frame, one for the training and one for the test. So you see the training has 119 rows and 1 column, okay, for the X, and then then also here for the test, it will return something smaller. I actually don't see where it writes it exactly. Okay, but we are going to receive everything in some. We're going to receive it in some container. So I'm going to put X train here, and then I'm going to put X test here, okay. And then I'm going to put Y train, then Y test, because this. Okay. So when it returns this, X train will contain the training set. X test will contain the train test set. Okay. Y train will contain the corresponding Y for the X train that was chosen, and Y test will contain the corresponding Y for the X test that was chosen. So if I do shift return, okay, then you can find the length of X train. And then let's print the length of X train and the length of Y train. X test, sorry. So it's 119 and 30. And you can check also that Y train and Y test, they have the same length also. And they actually correspond exactly to the same X train and X test. Okay. So it's 119 for X train and X test. And Y train and Y test is 119 and 30 also. And they correspond to one direct. So the next thing is just to do the fit. Okay, if you want, you can visualize your data. So yeah, you can visualize your data if you want. So let's plot a scatter plot. X string, Y string. So sorry. Let me see if this works. Yeah. So this works. I did the X string and the Y string. So if you look, it's almost like a straight line, maybe not exactly. It curves a little, so you have this. What if I have many columns for the X string, okay? And I want to plot Y string against one of the columns. So in that case, you can select exactly which column you want like this, okay? You put the column there, and you select the column that you want, and it's going to plot the column. In this case, it has only one column. So I plot it and I see the vertical is Y, the price of the house. The horizontal is square feet. Okay. If I do this smaller, to be able to see better. So what I'm going to do, we are going to do next is, and you can label it as you want. So let's do the fit. So first I create an instance of the linear regression that we imported. So if you look up here, you see we imported linear regression. So I'm going to create an instance of it. So I'll call this little LR. So little LR equals linear regression. Open this. So that will do it. Then I'm going to do the fit. So now this fit is going to use linear regression to use the fit on the X train and the Y train. Okay. It's going to do the fit. So it has done the fit. And we can plot the intercept and the coefficient. So the intercept is A0, the coefficient is A1. Okay. If there are many coefficients, it will print a list for you. Okay. So LR does intercept. So this will print the intercept, and then this for F. There's only one F in the for F. Okay. So it will print the intercept is minus 33, and the coefficient is 0.27. Okay. So if you want to find a house price, it turns out that you should use this coefficient. And then you should add 0.27 times the square feet times the floor area. So this is what you should do if you want to get the house price. Okay. How good is it? Is it very accurate? Okay. So these are one thing we can do. Let's plot the data first, and then oh no, let's do this. So once you already did the fit, you can make a prediction. So So let's say I want to make a prediction, and I know that the floor area is 450. So I can do predicted price, LR.predict, and I can put the 450 I want there. So what did I do? Okay, give me a warning. No problem. Now this one gives me an error. I think I know. I think he's expecting double like this. Okay, give me a warning. And I can now print the predicted price. So if your square area is 450, the predicted price is 90.22 square kilo. Sorry, $90,220,000. That's the predicted price. If you want for more of them, so let's say your house is 250 square feet. What did I do? Okay, each one has to be this. So I have to do something like this. Okay. So if the price is 450, then your predicted price is this. If the area is 450 square feet, the predicted price is this. If the area is 250 square feet, then the predicted price is 35.3 thousand dollars. So you're able to make a prediction. Well, one thing we want to know, more importantly, we want to know how good the fit is. So we are going to evaluate the error in the fit. Okay. So to do that, we're going to use the RMSE metric that we imported. So let's go up. So we imported the root mean squared error. So I'm going to use it. So I'm going to we are going to put in the training and the predicted values. So we have to first get a predicted value. Then we are going to use this. So before that, yeah. So let's do a prediction. So I'm going to say y predict. So LR dot predict. And I'm going to pass your X train to it. So this is going to give me the prediction. So Y prediction will be the prediction from the model. And it's going to use all this data that is there. So Y prediction is a data set. Okay. And it has all the prediction from these X values. And then I'm going to find the RMSE. Square error. So I'm going to put it doesn't matter which one you put first, but I'm going to put the train first, then the Y, the train you had before. So it's going to tell you, and then I'm going to print okay. So that's an error of like $11,500 in between the training and the prediction. Okay. So this is the error. And if you want, we can plot if you want, you can plot a data scatter plot of the training and the prediction and see how good it is. So let's do that. On the x-axis, I'm going to have the training. On the y-axis, I'm going to have the prediction. Then another thing I'm going to plot, I'm just going to plot a line a line so that if you're perfect, you'll be on that line. So I'm going to do this. Okay. So if you are perfect, you'll be on this line. Okay. So this is the scatter plot. So this is the scatter plot. I probably can, yeah. So on the horizontal is the training, and on the vertical is the prediction. Okay. Another thing you can do is, you see the RMSE is 11.5. Okay. For the training, what about the data we did not use for the training, the test set? Can we check also how good it predicts the test set? Okay, data that is not in the training, can we check how well it predicts? We can do the same thing like that. So first we are going to take the test set and we are going to predict. Then after that, we are going to calculate the RMS. So we expect that the test will have a higher RMSE than the training. So this, I'll call it Y test predict. And I'll go to put X test in it. Okay, and then I'm going to calculate the RMSE for the test. Is, I don't know the name, so I have to copy it. Is exactly this. Then I'm going to print it. Okay, root mean square. I need Y test predict. Oh, sorry. Let's put Y test first. It doesn't matter because it's just a difference. And it's squared, so we can do this. So print RMSE test. Oh, so this is actually does miraculously better than the training. So the test, the error in the test is less than the error in the training. Usually this is not what happens. So I think this is a fluke, either because maybe the data is too small, okay, to show this. But usually you find that the test has a larger error compared to the train, usually. But like you see in this case, is not the case. Okay. So can we improve the regression? That's the next thing to ask. And the short answer is yes, you can improve the regression. And yeah, the short answer is you can improve the regression. So the way we improve the regression in this case, instead of using another method, we still use linear regression, but we are going to try to let it use, let me see. So what I'm going to do is, when I plotted y against square feet, it's kind of like a curve. So I'm going to say what I want now is to extend it. Okay. What I want now is I want the same, but I want to use, say, the square of the area plus A2. times area squared. I think I know what to do. So I'll do A2 times area plus A2, and then I'll want area squared. Let's do area squared this way. Okay. It's not that you can do it. Okay. And you don't have to, yes, you can do it explicitly yourself and just calculate the area squared and then do a regression with two columns, so you can do that. Okay. But the interesting thing is, what if you have something beyond this? Let me give you an example. Let's say you have price is A naught, okay, plus A1 times area, okay, plus A2 times number of bathrooms or toilets that you have there. Next. Yeah, so you have this. Okay. And then the model is not great, but you want to improve it. So you want to improve it and have squares. So you want to have area squared. You want to have number of baths squared. And you want to have area times number of baths as your new variables. Okay. So in that case, so you want to have something that goes beyond linear. So you want to have area, number of baths, but you also want to have area squared. You want to have number of baths squared, and then you want to have area times number of baths. Okay. So just creating the two columns yourself, I mean, all the columns you need yourself will become cumbersome. With just one column area, it's easy to just say, okay, I create another column and do the fit. But if you have many columns for the linear regression, and then you want to add products, okay, then it will become cumbersome. But fortunately, there's a way you can do it with scikit-learn. So in this particular case where we have this area like this, we do something similar, okay, but we're going to introduce a new variable, and the new variable is exactly area squared. Okay. Well, we're going to use the functions of scikit-learn to do that. So a new variable will be there, which will be area squared. Okay. And this should give us a better fit. So the way to do that is to call a polynomial is to call this polynomial features and tell it we want something of degree degree 2. Okay, so I'll show you how to do that just now. So as usual, we're going to import something. So you don't have to do it by hand yourself. Okay. Import, sorry, from SQL. We are going to import this polynomial features. So I'll call it PF, polynomial features. So I will okay, let's import it first. Sorry, I missed it. Features. Oh, I got it now. Okay, then I'm going to create an instance of polynomial features. I'll call it PF. So it's
Please, we are still seeing the last.
Oh, sorry. Thank you. Thank you, Christian. Yeah. So now, from sklearn preprocessing, I imported these polynomial features. And then I'm going to create an instance of it, polynomial. And I'm going to put that the degree is 2. You can go on the scikit-learn website to see more about how to use these polynomial features. So I put here that the degree is 2. So it's going to create all products, everything of degree 0, degree 1, degree 2. Degree 0 is A naught, degree 1 is the area, degree 2 is area squared. And if, let's say you had the columns U and V, then it's going to create u to the 0. You're going to create u to the 1. And then it's going to create u squared. It's going to repeat, because u to the 0 is the same, it's going to repeat this for v. And then it's going to give you a product also, uv. Because all these other ones, u squared, okay, v squared, and uv are polynomials of degree 2. Okay. And then v to the power 1, u1, polynomial of degree 1, and then u0, which is just 1, is polynomial of degree 0. So it's going to create this. Let's say you had 2 features. If you had 3 features, UVW, then you can see how many combination it's going to create for you. So we instantiate this way. Okay. Then I'm going to create a transformed X for X train. So I'm going to use this polynomial feature that I created. I'm going to say it should fit and it should transform. So it doesn't do the linear regression. This just means it should create, okay, this just means that it should take the X train and do all the things it has to do and put everything in X train transform. Okay, so X train transform will contain, at the same time, it's good to do it for the test also. So that when you want to check how well the test is, you can easily do it. So here I'm going to say it for the test. So it does this. If you want, you can print X train transform. So it returns numpy array, and the first column is 1 because this is just a constant. This is the square feet that you gave to it, the area, and you can check this is exactly area squared. So it does this automatically for you. So the next thing we're going to do is we're now going to do a fit. Okay, and we're going to do a fit with the train transformed. So is LR dot fit X train transform, and Y train is not transformed. Okay, so it's going to do the fit for us. Okay, so it did it. We can try to calculate the intercept. We can try to calculate the coefficient. So this is the intercept. The coefficient is 0, and for A0, and then it's minus this for A1, and it's 0.00 this for A2. So this is it. Now we can make a prediction and say Y prediction. If you like Y train prediction, so it's LR dot predict. I'll take X train transformed. Because I think that was what we used. And then at the same time, I'd like to do the one for the test also. So that when you calculate the RMSE, you can easily check. Y test transform. So it does the prediction, and we can calculate the RMSE. I'll just calculate the RMSE straight. How do we do this? Is root mean squared. And I'll put the test and the predicted together. Okay. And then I also do the one for the uh, oh, I need the one for the training also. So let's put that first. I train. Okay. So the RMSC has reduced from 11 to 7.97, and this one has reduced to 9.0. So if you like, you can plot the price as a function of the floor area. For the training, let's do that. PLT does get and we can also plot the okay. Let's just plot the scatter plot. There's a way to plot the model, and you'll see there's a curve. But that takes a little bit more for me to explain. So we can plot y right? Y so on the x-axis I want it to be y predict. And on the vertical axis I want it to be the trend. Sorry. The x-axis I want it to be the trend. On the vertical axis I want it to be the prediction. Then also I'll do the y trend. Sorry, I want a plot. So to show me the straight line. So I do that. Okay, you can't tell exactly, but this is better than what we had before. From the RMS, you can see that the RMS went from 11 point something to 7.9, 7.98, and that one went from 10 point something to 9 point something. So it does indeed do a better job. This one also looks better. There's a way, like I said, to plot the line. Well, you need to do a sorting and everything. Let's try to just plot something that's not great, but we just plot scatter plots. I want to plot, but I don't want to plot with a line. I want to plot with points. So let's just do this. Y train. I want to plot it against X train. But I want to plot just the, sorry, X train should be here. This will not be great, but at least it will help us to see what's happening. And then what I want to do is Y predict. And then X train, I want to plot the column that has the I just want to plot the column that has the X Okay, so I don't remember the column. So it's floor area square feet. Okay, that's the only thing that's there. So I could just have plotted it because there's only one column in extra. So I could plot this. Let's see what happens. Sorry, yeah. I didn't put anything there. There's only one column, so I don't have to specify. So let's see what happens. So you can see the prediction is the orange one, is like it's the curve. Because it used the what did they use? It's a curve because it's used. Okay, let me try to do this. If I want to show, then I'll use show. If I want to print, let me see. I want to plot a safe fix, sorry. So not I'll call it plots.pdf. It doesn't show us anything. But here it should have my plots there, the PDF. Yeah, so I have my plots there as a PDF. So I'll go there and open it so you can see what is there. Okay, so this is the plot. You can show a grid and everything as you want. Okay. So the orange line. Okay. So the orange line is the prediction. Okay, so you see it follows a curve because A naught plus A1x plus A2x squared. Okay. And then the dotted line is the data. So I think it does better than the straight line. So this is one way that one could improve the RMSE. Of course, someone could say that, well, the RMSE improved only a little bit, not too much. Okay. And I will agree with that. It wasn't like cutting it in half, right? So if you look at the RMSE, before we had like 11 point something, and now it reduced it from 11 point something to 7.97. So it reduced to 8 from what did we have before? Let me check. Yeah, from 11.5 to 8. Okay. So you save $3,500. Okay. So you save $3,500. Yeah. So this is still quite some money. So the fact that you do a better model. Okay. And then for the test, the test became worse because it was 10 before it became 9. Okay. So some will say the better one to look at is the test. Okay. There's a way you can do something called cross-validation. Okay, we won't go into that. But
Prof, we are not seeing your screen again.
Sorry. Did you see the plot that I showed? Yeah, I think you saw that. Okay, so the error is 8. Okay, so this is like $8,000. And before it was $11,500. Okay. And then that's for the training. For the test is 9,000 before it was 10,000 if I'm correct. So let's see what we had before. Yeah, for the test it was 10,200. Now it's like it has reduced to 9,000. So some will say which one is better. Is it to look at the training or to look at the test? I'll say to look at the test. I expect this to be more accurate because it's data that it has not seen, then it is this. Okay. But there's another way you can do it also. You can do something called cross-validation. Okay. So you can split the data. So the test training data, you can split it into 5 groups. So this is called the 5-fold cross-validation. And then you do the model 5 times. And in each of the model, when you create the model, you take only 4 out of 5 of those groups. So if the first time you leave group 1, the second time you leave group 2, and then you do a model with the other 4 groups. The third time you do group 3, you leave group 3 and you do a model with the other 4, and then you continue like that 5 times. You find an average, and typically my experience has been the average will be close to what you get for Y test. The root mean square error that you get for the test set. Okay? So you can do a cross-validation that way. Yeah. Okay, so this is simple linear regression, and there are other methods that you could use. So there's random forest, and there's clustering, K nearest neighbor. So we won't go into that now. So what we'll do now is, let me look at the people that are. I'll send you a few documents that you can use to create projects that we can work on. I already have some projects that I think we can work on. So I'll send you a few of those documents so that then you can decide which of the groups you want to be in, and we'll try to do a few projects. I know when I send it to you, the project will probably have a timeline of 1 year. Well, let's look at it and think that maybe we can do it in 6 months. Yeah. Part of it is really just getting the data, and this is a lot of work. But I'm hopeful that some of the data, sometimes some people have done the calculation online and we can just use the data. Yeah. Okay. So I think I'll end here. If you have questions, you can ask.
Thank you, sir.
Okay.
Thank you, Prof.
Yeah, sure. Yeah, thanks.
Yeah. Sir, Prof, is it better to, I've seen some machine learning where at the beginning they import most of the libraries that they want to use. Which one is better? Is it why you are working, or it's better to import most of the library that you are using at the beginning?
Yeah, actually, I think my preference is to import all the libraries you need at the beginning. So at the beginning, you already anticipate that you're going to plot a graph. So you plot the matplotlib. I'm going to need this scalar, so you import all of them at the beginning. Yeah. So it's usually better to do that. You import everything at the beginning, and then you call them as you, and then you call them whenever you need to use them. So I think this is better. Yeah.
All right. And also, sir, at what point is convolution matrix is needed?
Oh, okay. So, now we did only regression. Okay. When you do classification, then you need to plot the confusion matrix. So for classification, because you're classifying things as either true or false or positive or negative. So for classification, you will need a confusion matrix. Yeah.
Okay.
But for regression, yeah.
Yes, sir.
Williams.
Okay, so concerning this regression, the error checking that you focus on mostly is the MSC. Is that the only error? What's it called? Checking the mean root means. Sorry, the error for
Yeah, so there are other metrics that you can use. So sklearn regression metrics. So let me share. So if you do a search for sklearn regression metrics, I hit enter, it will tell me metrics and scoring function. You can already see all the ones that it has listed here. So hold on. Which scoring function should I use? So if you go here, it will, so for regression, for classification, you can use log loss, 0, 1 loss, Brier score. For regression, you can use squared error, positive deviance. All these ones you can use. I think if I go down. Yeah. So if you go to this page, it can tell you all the different metrics that you can use for regression or for classification. Yeah. So this is what I usually do. So it can give you R squared value, which is so there's squared error. I'm trying to think. So there's mean squared error. There's root mean squared error, which we didn't do. There's mean squared logarithmic error. Mean absolute percentage error. So it can give you this also. Yeah. So there are different ones that you can median absolute error. It can give that also. So there are different metrics that one can use. Yeah. But if you just go to please search for scikit-learn metrics, then it will give you quite a number of metrics that you can think about using.
Oh, all right, sir.
Okay, so I'll send this short documents about projects to us. I'll focus on projects in material science, condensed matter, chemistry, okay, because I see the people that are here. Let's say there were some people that were in geophysics or atmospheric physics. Yeah, then one can do something like that. For instance, weather prediction. So you can try to predict the weather for tomorrow and the day after. You can do that also. Yeah. So, but we are mainly people in physics on this matter. So I'll send something related to this. Okay. So thank you very much to everybody. The recording will be in the same place in the playlist. So this will be day 6. And then you will be able to watch it after. You can send an email to me to ask questions, and this is fine. Okay. So have a good weekend. Yeah.
Thank you. And you too, sir.
Thank you.
Thank you.
Thank you, sir.